Okay, so today we are going to talk about classification. We lastly have seen one technique of classification, but today we want to continue with a couple of different algorithms. So what we've seen so far, we've talked about the regression, we talked about the model evaluation, we talked about the how we can do the prediction, but we said that we can use machine learning techniques to have classifications. So for classifications, we have, since we are talking about supervised learning, we have some labeled data. We already have classes of data, and we want to talk about, okay, if we have new sample, which class it is belonging to, and we want to see what kind of techniques do we have and how we can use it. So the applications are diverse, from medical up to like robotics and computer vision. For example, you have an image of cat, image of dog, and different animals, and you want to say which class it is belonging to with machine learning algorithm. So you want to say, is this human? It is not. And we want to talk about these today. So as outlined, let's see what we will discuss in detail. We quickly have a look at classification problems to remind you what is it. Then we talk about logistic regression as one of the famous techniques that we can use it for classification. And we will see how we can train it by gradient descent, this step by step. We talk about the sigmoid function, what is it, and we define it. We will talk about maximum likelihood estimation, MLE. We will see how we define it and how we can use it in logistic regression. Then we go through the most basic algorithm for classification, and one of the most well-known and practical one, K-nearest neighbor. We will see step by step how it is working, but the most objective of discussing K-nearest neighbor is to see how we can evaluate classification models. So we discussed about different metrics to see how the performance of the prediction is. But now today we want to see, okay, if you have classification problem, can we use same metrics? Some of them we can, but some of them, most of them we cannot. We should have some good evaluation metrics in order to say how good is our classification algorithm. So meanwhile, we will talk about the confusion matrix. We talk about the accuracy. We talk about the precision. We talk about the recall, F1 score, and we talk about the AUC-ROC metric. That area under the ROC will be the metric that we will see how we can use it for classification that we have. So these techniques are very common to use in any advanced classification algorithm that we will learn, so that be careful to catch them what they are doing. So any questions so far about today's class or previous class? Everything is clear? Hope you studied last week clearly, because now we are going to use it a lot. The topics that we've had last week, from gradient descent and stochastic gradient descent a little bit. First of all, let's answer what was the classification problem. As I stated, the goal is predict the class or category of the data that we have. We already have some samples, and based on the samples we have the label, we know which class these are belonging to. Then based on that, we want to train the data in order to do classification. So actually what we are doing, we are learning a mapping function that maps the input to the labels. So image classification is kind of, there can be many applications. For example, here can be used on image processing, that you get image as an input and you want to classify it. So there are different popular algorithms for image classification. We have naive Bayes, that is based on the Bayes optimal classifier that we discussed already, if you remember. That's like modified version of that that is more practical and can be used on different techniques. Logistic regression, K nearest neighbor are two that today we are going to discuss. Then we have decision tree, we have the random forest, we have support vector machine, SVM, very famous one. We have family of neural networks that we will have a look later on. That with neural networks, of course, you have done, most of you, or you are doing. You will do that. You can use it for not only prediction tasks, but also you can use it for classification with some modification on it. And we have gradient boosting. That is also one advanced technique. As far as we have time, we will discuss some of these. Then we move on to more complex problems later on. So today we are going to talk about logistic regression and K nearest neighbor. If we start with logistic regression, we can say it is a popular machine learning approach that is a supervised learning algorithm for binary classification problems mostly. It means that we have labeled data. We have some data sets that we are going to use those labels. And what we want to do simply, we want to predict the probability that the input example belongs to one of the classes. So it means that my logistic regression is going to give me the probability of how likely the new data is belonging to which one of the classes. And based on that probability, I can make decision to say, okay, if the probability is higher to belong to class A, I can assign it to class A. And based on this also we will discuss a new metric that later on you will see. So that how that probability threshold can be varied. It is a simple and efficient algorithm, and we can train different large data sets with many features with it. And also it can be used on image processing and many different complex problems. Later we will discuss the advantage and disadvantage after seeing whole algorithm. The whole concept that we will discuss is similar kind of to linear regression, but how we do that is different. Let's see how this is happening. And as I mentioned, a logistic regression can be trained by gradient descent, stochastic gradient descent, or different family of the optimization algorithms that we can have over there. So logistic regression is working by modeling the relationship between input features and output, and it uses logistic function. Logistic function is known as Sigmoid function too, that today, next slides, we will see how this is working. As I mentioned, this is similar to linear regression, and it can work also with continuous data. So you don't need to be worried about that, and that when we have classification problem, if the data is continuous, numerical, will it work or not? Of course, it will work. For example, we have, if we consider that we have an example of the input age, smoking amount per day, week, month, doesn't matter. The gender, the amount of overweight that person has. Then classes can be diseased or not diseased. The chance of heart attack, not chance of heart attack, that person have had heart attack or not, or lung disease or not, because like we have record from hospital, we know these data, for example, for 1,000 patients, and we know that this guy had disease or not. And with logistic regression, we want to see if you have these data, and if you give my information, my class will be diseased or not diseased. So first, let's answer why we cannot use linear regression directly for classification. Because we were doing prediction over there, right? We had some data, we were doing prediction. Why we cannot convert it somehow to use it as classification problem? we say, okay, let's have a quickly look. Linear regression was similar to this equation, y hat of I equal to intercept and the slope of the x added by some error. That we already discussed it pretty well. But how that was looking like, that was looking like a line that was predicting our data, whatever it is. Now, the problem that we have classification problem. If you look at the data range here, the data range is kind of can be randomly anything in any range. But in classification, what we have the data in class of 0 and 1s only. Right? If you have binary classification, we have only 2 classes, let's say. So when you have only 2 classes, whatever data have is like in class A, class B, class 0, class 1. The data looks like that. And what if we do linear regression? Then you can find a line like this, right? Let's say this is the best fit line for this data over here. But can it work? Because this line also is continuous. If data comes from here, the prediction line most likely is something wrong, and here also something like different or wrong. So that we are limited over there in order to use linear regression for classification tasks. So that in logistic regression, we want to find the probability of the occurrence in range of the between 0 and 1. Kind of we want to improve the linear regression over there. So what we do in order to achieve it, we use sigmoid function or logistic function. So it is like common to use both names. We can call it a sigmoid function or logistic function. That is a mathematical function that maps any real valued input to values between 0 and 1. So whatever input is, it maps the value between 0 and 1, and this is what exactly we want for classification tasks. It is commonly used in logistic regression, other binary classifications, in deep learning models, and many different techniques. And actually, it is doing the modeling the relationship between input features and output variables. How does it look like? It looks like this, a sigmoid function. So if you look at the plot first, the plot shows that, so this is the x. It can be from minus infinity up to positive infinity. Whatever the value is as input, it comes into range of 0 and 1. The output of y, the output of this model will be between 0 and 1, whatever you give. So you give some data here, it gives something near 1. You give something close here, it gives something like higher than half of the plot. How we show the equation for that sigmoid function? The sigmoid function equation can be written as h of the x is input, equal to this term over here, 1 over 1 added by e to the power of minus x. So it means that as real valued input, whatever I give to this function, the output will be between 0 and 1 for me. So this function, we want to use this function for logistic regression, but this function, as I mentioned, can be used in, for example, deep learning techniques. Later on, I will mention it. Why we use it there, for example, there the weights are growing, the numbers are growing. One of the purposes to limit the growing the numbers of the weights of the network that you are, in every layer you are calculating, if you want to recap over there. But anyway, now we want to kind of find a way to bring this idea to logistic regression to use it. Now how we can write that sigmoid function in terms of being used in logistic regression? We say we want the probability of dependent variable to be 1 given input that can be written in logistic regression. What does it mean? It means that, so in probability, you know, like the probability of this device in my hand is black is 100, right? 1. But if I want to say the probability of being white is 0. So the probability has two sides. So we need to discuss in one side. We just say probability of being 1 always, for example, in this example. We will discuss it in that form. So how we can write it, write the equation? We can write that, okay, in logistic regression, we want to talk in form of probability. And how we can write it, we assume that we want to talk about probability of the y hat is equal to 1. What is the probability of this? So we say P of I in terms that y hat, the predicted y hat is equal to 1 given by the x's. The input comes. What is the probability of y being 1? How we can write that probability? Now we can merge the equation that we have and add the intercept and slope calculation from linear regression over here. So just we are replacing this x as linear regression model with intercept and slope. So then the probability of the y hat equal to 1 given by x's will be in form of probability, and we are using the Sigmoid function. So we just replace the x with the linear equation. How complex it is that we have. We already learned all the combination, multilinear regression, the combination with binary input and whatever. We just replace it over here. Now, we want to find the coefficients by gradient descent or SGD. What were the coefficients? These thetas. We want to find proper values to replace here in order to have prediction. Right? But something is missing still. Looks simple. We just adopted linear regression with this equation. Then we have logistic regression so far. But something important is missing. And what is it? Who can guess? No guess? Cost function. So we need to have cost function over here. And what is the objective function or cost function for this logistic regression? So can you have a guess? What was cost function in linear regression or nonlinear regression? I mean the regression models. We introduced different kind of cost functions. For example, one was mean square error, right? But can we use it over here? No. Let's move to the next slide. We say cost function. In logistic regression, we define like mean square error. We define R squared or different metrics. But if we want to use it over here, how it looks like, this is like nonsense, right? You calculate mean square error of these is like almost useless in order to use it. What we do instead, we instead using maximum likelihood. Maximum likelihood, in next slide we will see how generally looks like, is computationally complex. Instead, we will write mathematically equivalent equation way, that is based on the negative not likelihood function, that also known as cross-entropy. Here is a little bit confusion. We have three different terms that you separately hear or study in some different ways. I want to clarify for you that wherever the slide that we are studying, the equations that we are talking, also as known cross-entropy, also as known maximum likelihood, also as known as the negative likelihood function. So if you want to visually have a look, what we want to do, we want to have S-like sigmoid function comes to prediction here, S-like prediction on our data, instead of having line like this. So depends on data, the curveness of course can be different, the distribution of data, but also this is like only 2D dimension. If the dimension grows, we cannot plot it that easily, but the concept looks like that. Okay, now let's start with talking about maximum likelihood estimation, known as MLE. It is commonly used for estimating the parameters of the machine learning algorithms, and for example, the algorithms like logistic regression, neural network, NLP, signal processing, and computer vision. There can be also much more applications on these. The concept of the MLE is different from finding a mean square error that we have. Here we are going to use also probability, not just finding Euclidean distance of the error of the predicted line and the each independent data point that we have. That here we want to also show the error of the coefficients. And we say MLE can be directly used to be applied on logistic regression without a stochastic gradient descent, but it is costly. So it means that we are going to define a concept for maximum likelihood estimation that even doesn't need SGD or gradient descent. We can directly apply it. But since it is costly, we are not going to use it. We are going to use it mathematical equivalence to this term, and then later use it with gradient descent or SGD to find the optimal prediction for the classification tasks that we have. So how it is working? It is working by finding the best fit of a distribution, and we are going to use normal distribution over there. So most of you know what is the normal distribution. Where are the markers? Ah, like guns. Give me one more gun. So most of you know about the normal distribution, of course. With normal distribution, we can use it to use the distribution, the probability of distribution. That we have two important concept here: the mean of distribution that shows where the center of the data is, and the covariance of the plot that we have, how certain we are the data is over here, or how uncertain we are that we can have different different plots over here, like this or this. So for maximum likelihood estimation, if we want to use that concept, we have two steps. Basically, we just want to understand basically how it is working, the main concept. We want to find, first of all, the maximum likelihood. For finding maximum likelihood, let's say we have this data, just simply this data that it is in one class. Don't consider two classes together. Just in one of the classes, we have this data that distributed on X. And we want to have the likelihood. We want to have the likelihood that shows the mean of the that normal distribution over there for us. What we do, we start adding one normal distribution on the data from, for example, left side we start, and based on this mean, we calculate the likelihood, whatever it is. The value on the mean is like equal to here, but on the X, on the Y is like some value that we calculate. Then what we do, we shift it to the right. The same normal distribution, we shift it to the right. Based on this normal distribution, based on this data, we calculate the likelihood. And we iterate this procedure, shift it to the right, shift it to the right, shift it to the right. We calculate the points over there per each one. Then finally what we do, we get the maximum likelihood. So after you did this in first step, you know where is the more likely this normal distribution should be based on this data. And you see that here the density of the data is much more. So that this maximum likelihood normal distribution represents this data much more than the other ones. This one over here represents the data much more than the other ones. After doing first step, so as I mentioned over here, instead of mean, also we have the covariance. In second step, we need to find the standard deviation. We have different terms to discuss about that, variance, standard deviation. If you need it, just have a look and the math to remind yourself. So same data we have now, and now we want to instead calculate the likelihoods for standard deviation. What we do for the same points that we found the best maximum likelihood for the same certain point, we start with different standard deviation. Then we also change the standard deviation from some value, certain value, and we change. And each time we calculate also the likelihood for each one of those. So after you do this in different iteration, what you do again, you pick the maximum one. And based on this, what we can do, we can say what is the maximum likelihood, what is the best normal distribution that represents my data over there. Then all this procedure can go into the classification problem. But basically, almost in any of the practical algorithms for classifications, we don't use this technique because this technique is costly. Like how should be the step size, and all this calculation is quite costly, and mostly in practice we don't use it. What we do instead, we bring it in form of writing some mathematical equation that is equivalent to this procedure, then optimize it by gradient descent, for example, or any optimization technique that we can have. So as I mentioned, I stated on the slides that maximizing likelihood is difficult optimization problem. Instead, we write the optimization technique that we call it as minimization of the negative log likelihood function. So this function is important, very also useful in machine learning techniques. Keep it in your mind that negative likelihood function is equal to what we did visually over there for MLE, and it is mathematically equivalent to that. That objective is minimizing the negative likelihood that is called that also known as, whole this procedure known as maximum likelihood estimation, and also finding the coefficients of the thetas that we have, and also known as cross entropy. So one equation has three meanings or three definitions over there. Now directly, meanwhile we want to see it, we also want to apply gradient descent on it to see what are these steps and completely solve logistic regression. Similar to last lessons course, what we do, first of all, we have step 1 to apply gradient descent. We first initialize the parameters randomly, so that, for example, we initialize theta hat 0, theta hat 1 to, for example, 0, or some random values. Where we do it this time we do it in sigmoid function that we've written already in this over here. Okay. So the theta hats will be some random value because we don't know. And we want to calculate based on this the probability now. In step 2, what we need to do calculation of the cost function. The calculation of the cost function, as I told you, maximum likelihood is costly. We want to replace it now. what we do, we can use gradient descent to minimize negative likelihood, and negative likelihood is cost function that can be written in this form. If I directly go to equation, how it looks like, it looks a little bit complex, but it is not. We say the j of the theta hat 1. If you remember, I told you that j or e represents the error in machine learning techniques. Especially is very useful in deep learning and neural network. Also, we write the function like j of the theta or the parameters that we have. So the error that over here we have can be represented as sum of the term over here. The p's, what are the p's? The p's are the equation that we've used over here. The probabilities of the sigmoid function. Come back. The probability of sigmoid function. We calculate log of them and times them to the y of the I, the true labels that we have. So sum of this log of the likelihood can give us the j of theta hat, the error that we have. So one point over here, why negative? Why we add negative? Because in maximum likelihood, we wanted to maximize. We choose the maximum point over here. But here we want to minimize the value over here. We convert it to minimization problem. In mathematical form, if you just simply put negative here, then we have minimization of the likelihood function that we had over there. I also stated one point over here that why we use the log, because we transform the product of the probability into some of the logarithmic, that it makes computations much more efficient, and we need less computational cost over here. That why that is happening. You should have a look at the mathematical proofs, but this is very common to use. We use it like in SLAM course. We use it in also in reinforcement learning in some stages, so that this is common term to be used. Now, okay, let's say we have sum of true labels times log of the probabilities, that this probability comes from those coefficients. We have it, we calculate the loss or the cost function. What we need to do in able to use it in gradient descent, we need to do something. We need to calculate the gradients, right? The slopes of the function, because this is only the cost. But we said that when you have cost function, when you have a slope of something, we want to find the slope of the cost depending on the change during time, because every time that you calculate this, the value is changing, and the value is changing. We want to find the slope, and based on that slope, we want to optimize it. So we need to apply the stage that we need to know. Also, I've written that here, this equation over here is known as cross entropy. This is very common to use it in machine learning. Later on also we will discuss it in different algorithms. So in step 3, what we need to do? We need to do calculation of the gradients that is coming from, in this example, negative log likelihood function, and we just simply can write exactly what we've done last lesson, the gradient of the loss function, gradient of the j of the theta hat. We want to find the gradient, so that we can write the gradient, and based on the gradient that we said, we should find the slope of this line based on each one of the axes that we have. Here in this example, I've shown that, so if you get the gradient of the previous function, you have the term over here. This time the difference, if you have a look different last lesson, the differences there the differences was the true value, But here we have the P of the I that is coming from, there the error was from the mean square error, but here comes from the probability of I, that this probability of I already calculated by probability of y hat being 1 by sigmoid function. So that we calculate the differences of this term over here, that is probability, by y hat of I. Then we can write the same equation by second axis by adding the times of the x. This is for intercept, this is for slope, and we can continue how many slopes we have. If you remember in linear regression, theta hat 0 for this one, and theta hat 1 times x1 up to xi. Up to xi, how many you have, you calculate the cost function, and then we have the calculations of the gradient. And in the next stage, what we needed to do, we need to update these thetas, right? The values of these thetas. And updating of that values of those thetas should come from what? Should come from step 4, that is showing us how we can replace theta hat 0 by new value. So theta hat 1 minus, again, alpha learning rate times the gradient that we calculated in previous slide. We replace it over here. For theta hat 0, for theta hat 1 we updated, for theta, the ice theta that we have in the model that we have, we replace it over theta. So what we are doing with gradient descent, we are calculating the coefficients of thetas to find that sigmoid function instead of linear regression, to fit it to our model of classification problem. So what we need to do, lastly, we just need to repeat step 2 to 4 until it converges. We do that as much as it converges, and there is like, you say, okay, number of iterations that I have for training, it finished, or the error is not changing too much, or those thetas that we are calculating, the loss function is not changing too much every time. So any question? Was it clear? The whole procedure is similar, same. We just change the cost function, and we change the probability. We bring it probability to a sigmoid function. We had two modification to gradient descent that we solved linear regression over. Now, as I mentioned, we can use, instead of gradient descent, we discussed gradient descent. You can convert it to SGD. I'm not going to explain it. You just can create mini batches to train the data, exactly same as previous. And we say logistic regression model can be used, can be achieved very good accuracy for image classification tasks, especially binary classes. You can train, like, give image of cat and dogs, like 1,000 of them labeled. You say this is cat, this is dog, this is cat, this is dog. Implement the same simple procedure, then you will achieve, if you give new image, it can give you that if it's cat or if it's dog. So, of course, you will have assignment 2 based on this one for next lessons, that you implement a classification problem based on what you want. It can be also image, and report the findings that you have based on also later today's course. How you report it, you will learn. But the task is up to you. Whatever you want, you can use it for logistic regression, and you can modify last week's course code. Just replace it by type of data that we have for classification and equations. But now, what are the challenges of logistic regression? We say it is working reasonably well if the even if the model is nonlinear. That works usually very well in nonlinear models too. But in situation that nonlinearity is very, very high, some other machine learning algorithms can perform better. that can capture nonlinearity much more. What we have, we can use decision trees, random forests, complex neural networks, or support vector machines to capture nonlinearity. That is if it's very complex there. So the question is why we are not going to study just one of the algorithms that is based in machine learning. Because we are developer, we must know underlying understanding of what's happening in order to understand the complex ones, and in order to be able to develop algorithms, to propose new algorithms, not just using black boxes, not just using one algorithm. So the idea, the motivation is like that. For example, whatever you're learning, you need to know about cross entropy. Otherwise, it's like shallow understanding of one algorithm that is useless. So that's why we are studying all these concepts. But also you can use them because logistic regression is very famous. You can search on different applications what they've used for over there. So any question up to there? Clear? Good. Now let's talk about the KNN, K nearest neighbor. I'm pretty sure most of you already know or have heard or even implemented. But let's have a look what is it visually. And the main objective over here is that we want to also see how we can, after classification, how we can evaluate our model. Meanwhile, also we are going to add evaluation of the models that we have. We say it is machine learning algorithm for classification that also is not limited for classification. We can use it for regression tasks. If somebody can tell me how we can use KNN for regression tasks, I can give positive mark. Who knows about KNN? Raise your hand. Raise completely your hand. Just one? Impossible. Really? Okay, I thought you already know. Then no expectation from answer. So let's see how KNN works. So then you should answer. Hugo. Okay. So this is like very beautiful. When you study it, then you say, okay, you should ask yourself, okay, I studied this algorithm, can I use it for prediction or is limited for classification? Today also we will see that if we use KNN, we also can use it for regression tasks to also predict something. And you see that very simple and very efficient. So first of all, KNN is non-parametric classification. It means that we don't want to find thetas or something. Those thetas are parameters that we were finding. We don't want to find that complex things anymore. KNN does not build a model during the training phase. We don't have even a model to build it. Because of that, it is simple and efficient in many tasks. What we do instead, we instead store the entire data. We need to have access to labeled data in order to use it to do classification tasks. First, we need to have the labeled data set in a supervised learning model so that we can use it. And if we want to answer before even seeing the algorithm, we say in regression task for KNN that assigns numerical values based on the average of the K nearest neighbors and target values. I think this is a little bit early to know, but the data that we have, instead of having classification, we just need to return the average value of that class. That we will, after a couple of slides, you will understand it clearly. I was assuming actually who already is here knows KNN because of that.
Trying to find like different samples and trying to find a point that is closer to some points.
Yeah.
Also, I think maybe it's possible by doing like for linear regression program to using linear regression program. And we have a lot of data points.
Yes.
So I can like find use one point and I say this is more closer to this part of the data set and this part of the data set. I can generate a line for it.
No, we don't need to generate line for it.
Oh, it's not doing this.
No.
Okay.
Any other question? Okay. Let's see step by step how it is. It's very simple but very practical algorithm. Also, this algorithm, be careful to make sure that you understand it. You can use it in hierarchy with different algorithms to boost the performance. You can use it with different optimization to improve the performance. It's common to use it in combination with other algorithms. So what we do, we say choose the number of neighbors, k, and distance metric. So first of all, we should define the number of neighbors and k. What does it mean? It means that visually I have many examples there, but let me also quickly draw something here. I want to enlighten everything for you. So we have some data, and we have the labels. This color indicates the labels. I know that these are the class A, B, like class blue or green, and this is my plot. The X1, X2, feature 1, feature 2, can be anything. Can be the, for example, the size, the price, for example. Size, price, something random. Or whatever. But I know that these are the labels. Let me also separate it a little bit. Now I want to define the, first of all, k. K means that, so each point that I have, how many neighbors? When I'm talking about k, I'm talking about one sample, and how many neighbors of that sample? Okay? And the metric, distance metric, says how I say that this is neighbor of this. What is the metric to measure the distance between these two? So, as I mentioned, parameters. K depends on the data set and should be adjusted. It means that, so when I'm talking about the K, like the neighbor of these, if I talk about like 1, 2, 3, 4, Y4 depends on the data set, we will see. Also, I will show you visually the differences of the algorithm if we change the K. On the other hand, the metric. The most basic metric that we can discuss it is Euclidean distance. Euclidean distance simply can give you the distance of between these 2 points over there on 2D dimension. If you have 10D, doesn't matter. It can give you the distance between 10D dimension of the data over here. The shortest distance, Euclidean distance, is like shortest distance between 2 points from here to there, for example, in real environment. So how we show the equation? Equation is like we have distance of point 1 and point 2, the coordinates of point 1, subtract the coordinates of point 2 in 1x, and here the second one, and up to the nth coordination that we have. If in mass, what we do, we can write, if we have like, let me maybe write it y, that maybe is on, this is not output, like x minus, so if we call it like this point as x1, I want to make sure that you all, and y1, the point and the other point, x2 and y2, then what we do, x1 minus x2 to the power of 2 added by y1 minus y2 to the power of 2. So this gives you the distance. And what is this distance? This distance is direct line from this point to this point. With this equation, you can find the distance between 2 points. And we can use the same concept in order to measure the Euclidean distance between 2 of the features and how many features we have if we have two data samples, P1, P2, 2 data samples. And these data samples can have like 100 features, dimension of 100, doesn't matter, we just like add it, then give you one simple value as D, says what is the differences between these data. So this can be our metric in KNN. Instead, we can use Manhattan distance. So you may say, okay, I don't want to use Euclidean distance. I want to use another technique. It is called Manhattan distance. Manhattan distance looks like this. So the same concept, but here we don't have square root, the differences between features of 2 points. Or we can use Minkowski distance, that this is another metric, that this metric is something in between Manhattan and Euclidean distance. So how it looks like equation, the equation looks like this. The distance between point 1 and point 2 is the sum of the point 1 subtracted by point 1 to the power of p, and this can continue also based on that. And finally it goes to the power of the 1 over p. That this p is different from this p1, p2. P1, p2 are indicating the data points, but this is a positive real value that indicates how much we should get close to Manhattan distance or how much we get close to Euclidean distance. And you can see that I've written, if the p is equal to 1, it becomes Manhattan distance. If p is equal to 2, it becomes exactly Euclidean distance. Based on that parameter, you can adjust how much you want to get close to this equation or that equation. All these three can be metric for our k nearest neighbor algorithm. So we simply use Euclidean distance, and it's very common to use. Okay? So again, what we need to know k, number of neighbors. And we need to know how we want to measure the distance between 2 data points. So far we know in step 1. Then what we need to do in step 2, we need to calculate the distance between all existing labeled data and each new data that is coming, simply. And by defining the k, for example, if we define k7, if this is my data set, and in this data set I'm indicating age and smoking record, two values, age and smoking record, and I say like this is new data, for example. If the new data comes, I calculate the Euclidean distance between this point and all data that I have in step 2. Okay, clear? Then what we do, we select in step 3, we select the k nearest instances so that this point over here is close to k nearest instances based on the Euclidean distance that I want. Which one of the points are the most closest one to this sample that I have? I can sort the distances between all data, and I can say which one of the points I'm closing to. Just one point over here, that if you look at this data, we have red and blues. That these red and blues, I don't know how much is visible, it's a little bit hard to detect, but if you can see clearly, so red and blues are indicating, for example, the heart attack. Age, smoking record, red ones, they have had heart attack, the blue ones, they haven't. That in data, if you look less age and less smoking record are more blue. Up there, more red. Also, the class of this sample is also calculated over there. In left side, in sample that we have, you can see we calculate all distances and we pick 7 ones. And the other sample that comes, for other sample, we calculate the distances between all data points and we pick the 7 closest ones. Why 7? Because k is 7. After that, what we need to do, we need to assign these data point to the maximum classes that we have. So I indicated, so this point are, if I choose 7 closest points, then look at the classes that they have. 1, 2, 3, 4, 5, 6 of them are red. They have had heart attack. It means that if new data comes with this age and with this smoking record, my prediction is that this data point is belonging to heart attack. On the other hand, another example, new data comes with like age 30 and this smoking record. and new data comes, I get I get the distance with all of the points. Then I pick 7 ones, and then I look at the classes. For example, 1, 2, 3, 4 with healthy one, that I say this is healthy class. But on the other hand, 3, 4 red ones. Is it clear? The algorithm is very simple. New data comes, get the distances between all, then choose k number of nearest one, and assign it to which one is much more. Now in regression task, we can return the average of the k nearest neighbors, so that we can say, okay, if we return the average number of these for age and for smoking record, this can be regression. Then I can return some value, right, as prediction. Or if I want to, like, depending on what I consider as output, I can get the just average of these values as return of the output, whatever it is. So in the example that we have, if we want to have a look for, again, data of the smoking, age, and heart attack, so here you can see with better understanding of like the red ones and the blue ones, and you can see that like these blue ones are healthy, those ones are heart attack. If we run it for k with equal to 1, we want to draw the decision boundary to see what is happening. So with k equal to 1, it means that I want to say, okay, each one of these data points, I only want to look at the one closest point as data point and draw the decision boundary. And for drawing the decision boundary, I want to color the whole environment by considering each one of these pixels, each one of these points on whiteboard here, I can consider as one data point, right? And I want to color it based on this data point over here is related to which class. And if I do that, I will have decision boundary, and you can see it looks like this. So the blue ones shows that this area, whatever data comes in this blue area, they have no chance for heart attack in our prediction in this, based on this data. On the other hand, red ones, all these red area shows the ones that have chance for heart attack, and this is called decision boundary, the boundary that splits the environment. As you see here, the decision boundary exactly splits the data. Even like one red line is over here, my decision boundary even split this to red one. But this is bad, right? What we call it? We call it overfit. This decision boundary is exact example of overfit. Why? Because one sample is here, this says like this is red. But this is supposed to be something exception, right? This guy is exception, this guy is exception over here. Mostly if you have like low amount of smoking record and low amount of low age, then you should not have that high chance for heart attack. So that shows that our K is not proper. So I've shown for K equal to 7. If we run the example with K equal to 7, we will see much more reasonable decision boundary. So that says, okay, left downside here most likely is blue, is safe, although I have some wrong predictions, but most likely they don't have chance for heart attack. 7. What if I increase it? K equal to 15. Still not bad. The decision boundary, you see that becomes a little bit more simpler. And if I continue it to 30, you see again left side is okay, and decision boundary a little bit more simpler. And if I increase it to 100, what is happening is like almost getting a regression line. It splits it into two. It means that to classify each one of these empty pixels over here, empty points, to color it, we consider finding 100 data points, like in circular form, 100 data points, so that say, then get the maximum, then put it over there. Clear? Now we want to answer, okay, what we should do to find the proper K. We say, okay, we can use different techniques in order to do that. One of the techniques is cross-validation in order to find proper K. That we can use, for example, K-fold cross-validation in order to find proper K. But for cross-validation, we need to have metrics that those metrics should be used. We can use, for example, Euclidean distance in cross-validation for KNN. And to find the optimal value of the K, we can find the average accuracy over all K iterations. Then report the accuracy of the K, then have it. If you want to train KNN with libraries, it is very simple. Just 3 lines. You import the library, define the classifier as K nearest neighbor, and feed the data X and Y. That's it. And of course, you need to say that, okay, my number of neighbors, how many? For example, 1 here. My metric is, for example, Euclidean or Manhattan. You just write the metric that you want. It works. But why we are learning this? Because we are learning to see how the background is working and how we need to implement from scratch ourselves. Actually, we are developers of libraries. In future, you should develop libraries yourself, not just use them. So because of that, we need to learn it to also implement it. So next, we will talk about the evaluation of performance, but we will have a break over there. One point before doing that, just I need to mention that here, the example that you see in these slides, I applied to make the decision boundary. We tried these data, so each existing data, labeled data, in order to draw the decision boundary. But the objective is find proper K, so that later for new data I assign the class. Don't forget this. But here, just we didn't use new data, or we didn't split the data with cross-validation, sampling, and do it on the data. We didn't do that. Just here, I wanted to visualize the decision boundary. Just keep this in your mind. Any question? Yes?
How we know that our K is already optimal?
How we know? We can use the cross-validation. With cross-validation, you sample, you train with K equal to something equal to 1. Then do cross-validation equal to 2, cross-validation equal to 3, and whole cross-validation should be run sampling many times, right? Splitting the data set to, for example, 5, and try with 5, then get the average. Then do it for second K, do it for second K. You try from 1 up to number of data that you have, consider all, then you pick the one that is best. Then you say this is optimal. Then one time you do that, then for that data set you have optimal K, new data comes, you classify it. And you don't need any model, you don't need any complex training model. New data come, quickly you say this is which class. Very efficient algorithm, many applications. I've also used it in practice many times for different applications. Okay, now we can have a quick rest, then later we discuss the evaluation of performance of the classification, because that's different from regression models, prediction models.
That's the best kind of approach.
Okay, everybody, let's back to class. Everybody, hello? This class is big, but design is bad. It's wide. Okay. So far we discussed about a couple of classification algorithms, right? But in classification algorithms, if you have a look, for example here, if I bring the decision boundaries, for example here, how can I say how good it is? If you have a look, for example, this data, red data point here is in middle of the margin. These blue ones are correctly classified, these red ones are correctly classified, but some of them are wrong. How can I say how good my model is? We should learn some new ways that we should be able to use it in classification tasks in order to report our performance. Some kind of metrics. That today we want to see the most important ones. And I was like, if you know about classification, is like almost a must to know these techniques and must know how to read it and understand how that looks like. So what we have confusion metrics, we have accuracy, we have precision, we have recall, we have F1 score, and we have area under the ROC curve. So that today we want to understand what are these. May look a little bit confusing and complex. Actually, if you understand the confusion matrix clearly, then that's it. We just apply some equations in order to use that confusion matrix output to calculate what we want. So let's dive in one by one. We say confusion matrix is the most common evaluation metric that evaluates the performance of the classifications algorithms. Doesn't matter how simple algorithm it is, how complex it is. We need to report the confusion matrix most of the time. If you study also papers, you will see many confusion matrices inside. That is similar to a table like that we use to evaluate the performance of the classification algorithm, and it summarizes the number of predictions that we made by classification technique. It's kind of counting how many wrong, how many true we did classify, but in formal way that we will see. So if we want to specifically also talk about one example to understand it clearly, we should define 4 terms over here. We start with true positive, TP. True positive based on the disease example, we say if the model predicts a patient has a certain disease and the patient actually has that disease. That is called true prediction or true positive. My model says it is true and really it is true. Very clear, right? On the other hand, we have false positive. The false positive says, if, for example, my model says, patient has a certain disease, but the patient actually does not have the disease. The reverse of that. In both cases, my model says, yes, it is true, or he or she has disease. But in first case, really it is, and second case, no. How we know? Based on the label. We have the label, we know the label. Now what about vice versa of this? Simply, we say true negative. In true negative, my model predicts that patient does not have the certain disease. Actually, he or she does not have to. So it's like red side says no, and it is really no. It's false or it's really false. And also we have false negative. We show it as Fn. We say that if the model predicts the patient does not have the certain disease, but patient actually is diseased. Two side of discussion. From true side, that is true. From false side, that is false. And from true side, that our model says It is correct, but it is not. It's like prediction is wrong, and here is prediction wrong. So then when the prediction is wrong, if you want to remember, first word is F. First word is F, prediction is wrong. First word is true, prediction is true. From both sides. That's kind of trick to remember it. Clear? Now, let's have the same example. We had the example of the k equal to 7, the data set for age and smoking records, and we have with k of 7, we have this decision boundary with KNN. Now, what we want to do, we want to draw the confusion matrix. What we do, we draw this plot over here. How this plot is looking like, this is exactly the result of that data. How this is looking like, the matrix includes like this: true negative, true positive, false positive, false negative. This is a standard way of showing the confusion matrix, first of all, for binary. If we have more classes, then this row and columns is growing to represent the same concept. Then we have multiple of those based on the comparisons. So what the color means? The color means that is indicated here. Shows the numbers, how many of true negatives I have here. True negative, you can see how many I have. True positive, you can see how many I have. False positive and false negative, you can see how many I have. And by looking at the confusion matrix, what can I understand? I told you, keep it in your mind, truths are my model prediction, right? My model prediction, if it's true, you can see that the red and orange line is high. When it's false, my prediction is wrong. These blue ones, the numbers are low. And what quickly I can understand, my classification algorithm works almost good, right? Because falses are low, truths are high. Then you have a classification model, somebody reports you or you report the result. If I ask you, invent new algorithm of classification, how complex it is, what have you done? I finally look at this and I understand how good you are. Let's say I give you assignment with a data set, then I say every of you, you should implement one classification algorithm. How can I know that which one of you are the best? Just looking at this confusion matrix. Clear? Simon, is clear? Okay. Now, confusion matrix. Here we performed on the, like this confusion matrix performed on the, again, that's just all exact data that we have, not the samples. But usually we should do cross-validation, we should do the sampling, and based on the test data, show the confusion matrix to keep in your mind. Here, just I showed on clear exact demonstration over there on the data, on the trained data. Now, let's, based on that confusion matrix and based on false positive, false negative determination, let's say, okay, how can I report a value for accuracy? Although that's very clear visually, but I want exact value. How can I show? I can show the metric accuracy. The accuracy shows the overall proportion of the correct prediction that we can calculate it by this term over here. Accuracy is equal to true positive added by true negative times over all the sum of all of them. True positive, true negative, false positive, false negative. I just divide, again, simple, true, my correct predictions. Correct predictions over all. Then it gives me accuracy. I can report the accuracy value. On the other hand, precision and recall is very also famous. If you open a research, any research that is classification, for example, you study YOLO's paper, you will see that they are reporting precision, recall, and confusion matrix. I don't remember exactly, maybe they don't, but they should do, whatever. So precision is measuring the proportion of positive predictions that are correct that can be calculated by this. Precision is true positive over true positive added by false positive. This gives me the term precision. That again, it shows the positive predictions are correct. How much positive predictions are correct? Precision. And on the other hand, recall shows sensitivity of the true positive ratio, and it measures something similar. That equation is precision is equal to true positive over true positive added by false negative. Just simple calculations, catching up the ratio of the how much is correct based on those true and false predictions that we have. And here it indicates the actual positives that are correctly predicted. Should be very clear. Next metric is F1 score. F1 score is for classification, and it combines the both precision and recall together into one single metric, so that we can show in combination. And it usually the basic iteration is F1 score is equal to 2 times of the precision times recall over precision added by recall, and this gives me the F1 standard metric as a score. So any questions so far? Clear? You just calculate the confusion matrix, then calculate the metrics. Should be some lines of simple code. And of course, libraries you just ask gives you all together. You don't need to even calculate. But now we want to talk about area under the ROC curve, and let's see what it is. We say the ROC stands for receiver operation characteristics, that we plot a curve as true positive rate on the other side against the false positive rate. So we want to have a plot that shows the TPR and FPR. We will see how to calculate this ratio, true positive rate and FPR. This is similar to precision for different thresholds. So different threshold means that we want to define some thresholds that threshold should be vary, and per each threshold we want to calculate the ratio and plot something to understand how good my classification model is. So we say, okay, let's break it one by one, step by step. We say AUC-ROC metric is ranging between 0 and 1, and the Y indicates perfect performance, and 0.5 indicates random performance. What does it mean, random performance? It means that if I have binary classification, class A, class B, I have no idea of what are the classes. You ask me question, I randomly say A, B randomly. So that's like, if your classification, you apply some algorithm on classification, and you apply this metric over here, AUC-ROC, then the output is 0.5. It means that your classifier is completely random function. It does not learn anything. Just randomly says AP. But 1 is the perfect. On the other hand, what if, like we discussed, 1 is perfect, 0.5 is like random? What is if it's less? If it's less, it's terrible. You did something worse even. You proposed a classifier that even does worse than random. Predicts wrongly completely. Learn kind of other way. So it's like I asked this guy over here to propose classification algorithm, and later I asked, like, report me the result, then I see that the value is less than 0.2, and he says like, that's very good, you don't know. It works perfectly fine. And I look at this number, I say, so even it's worse than what could have been random. So now, first of all, let's define two of the ratios, TPR and FPR. So this says that, okay, it's exactly the same equation as the precision, that TPR says the ratio of the true positive over true positive added by false negative. This is comma, this is not upstroke. So that looks like that this comma. It is the ratio of the true positive to the total number of the positives. On the other hand, we should calculate the false positive ratio, that says this time false positive over false positive added by true negative, that is ratio of the false positive to all negative ones. We calculate two ratios, for positive ones, for negative ones. Now we want to use these to calculate the AUC-ROC, one calculation, and one also curve. Any question? Is it clear? Now what we need to do, we need to iterate a threshold between 0 and 1 and calculate the probability that we consider that the prediction is belong to positive class, and we consider a sample is belonging to positive class that is greater than 0.1, 0.3, for example, 0.9, 0.79. What does it mean? It means that I want to create a threshold. I state for you that. So in probability, we have two classes, and we say, okay, the probability of this being black, right, being 1. Now, what is the threshold? I have a value, right? Like my model says like 0.2, 0.6, 0.7. As human, we say everything above 0.5 is we belong to higher class and lower class. We automatically do that. But here, since we want to plot and since we want to calculate this metric, we say that, let's say from 0 to 1, the threshold, I want to increase it, and each time that is higher, I say, for example, is belonging to class 1. So it means that, like, even here, 0.1 says that if it's higher, then belonging. 0.3, then I increase a value from here to here. And the step size is depending on me, usually 200 in this metric. So from 0, I increase there, the threshold of the probability to be into class 1. Then what I need to do, then I can plot it, the ratio. Each time, for each threshold, I can calculate the false positive rate with the equations that I gave, simple equations, and true positive ratio. And if I do this, here, we have the reference line that shows the performance of the random classifier. This is random classifier. And this blue one that is hidden almost here, it is 1. That is maximum. ROC curve, blue one, that is maximum. Why this is maximum? This is maximum because k is equal to 1. In the same example that we had for k nearest neighbor, k is equal to 1. K equal to 1, it means that exactly my classifier says which one is which one. 100% predicts perfectly. Because of that, so because the decision boundary, if you remember, exactly was splitting and clearly saying which one is which one. So that my accuracy is 100. Accuracy is the maximum. Then this is 1. When this is 1, the false positive rate. In contrast to true positive rate, you can see that it is on the maximum edge. What if, to understand it better, what if we increase the k? It means that our classification is not that accurate because this is overfitting actually. What is happening, before explanation, you can see that if I calculate it for k equal to 7, For a false positive rate. On true positive rate, it looks like this curve. Now I can say, based on this, how much my curve is close to up left side corner, it is better, right? How it gets close to this red line, it is worse because it gets closer to randomness. Visually, I can really read output of my classifier performance. And if I do K100, you can see that even it's getting closer to randomness much more. So the same point here, nothing specific. Any question? Is it clear? So this is very useful metric, a little bit confusing, hard to understand. If you use libraries, one line of code, two lines, one line for score. This is score, I will show you next slide how we calculate this is score, this is score, this is score, and the curve is over there. You just need to plot based on the changing the thresholds. And don't mix that thresholds with this K. This K is different. That threshold is the value for probability. Any question? Okay. I noted over there that usually is 200 iterations for that one. Now if you want to see how we can calculate the value has an equation like this, that it is a matrix or array that these indexes are showing the same probabilities, and we just calculate this term over here in order to have one specific value that was on the plot over here. This value can be calculated by this term over here. I'm not going to prove it, why it is like that, why it is working, but if you are interested in, it is known as trapezoidal rule, that is numerical iteration method for approximation, that we are approximating integral instead with this one, the area under curve, because we need to know the area under curve, for example, here. We want to calculate it. So that's the mathematical equation. If you are interested in, you can study in depth of the math. But if you want to use libraries, it's like you just from sklearn, you just import it, the score, and import the curve, and that's it. Curve gives you the curve, score gives you the these whole calculations as one value that you can plot. We just want to see the maths, but we don't want to prove it how that works. Now let's put everything together visually to understand, to see. For k equal to 1, we saw the sample. And now I drawn the confusion matrix for you. You can see how it looks like. Here k is equal to 1, precision is very high. You can see that the red ones is very high. You can see accuracy is equal to 1, maximum. Precision is equal to 1. Recall is equal to 1. F1 score is equal to 1 because no error. And AUC-ROC score is equal to 1 too. On the other hand, let's decrease it to something reasonable, k equal to 7, a model that is for classification more reasonable. Accuracy is decreased to 0.82. Precision 0.88. Recall 0.74. F1 score 0.80. And AUC score 0.87. So we have better, like is not overfitting and kind of reasonable model. On the other hand, let's make it worse. Look at also here. The confusion matrix, the number scale from 20 decreased to 15 over here. And wrong ones are increased over here. And here, if you look at right, again, it is decreased, the confusion matrix value, and accuracy also is decreased, but not too much, because still this is reasonable model. You see, still you can split the data reasonable, although the k is not good. So whatever classification algorithm is, you are proposing very advanced technique for image processing in machine learning, and you're beating the best existing algorithm in the world. How you show your performance? You can use these metrics to show your algorithm performance. You can report it on papers then, publications. Or you want to read other research to understand it, you can quickly have a look at the confusion matrix, you can understand how it is working. Any question? Again, perform this on test data. You should do cross-validation. I'm just showing here a sample of really what's happening there. We usually, when you are testing the model, you need to do it on train and test, and do it on test with cross-validation, not just showing exactly your model's output. Also keep that in your mind. So what we've seen today, we understood the logistic regression, how to train it with gradient descent. We understood maximum likelihood estimation, and if you remember, it was based on the negative log likelihood function. Also, we call it as cross entropy. So it's very common to use cross entropy. When we say cross entropy, we mean the same equation calculations. We learned how KNN is working, and we saw how we can evaluate the performance of the KNN by confusion matrix, accuracy, precision, recall, F1 score, AUC-ROC in two terms, value and curve. So that's it for today. You just have a small practice. The practice is you need to do implement KNN yourself, not just that 3 lines. Implement KNN. First, choose your desired problem, whatever you can consider. Then generate some data. Data can be like 10. You just can, like you say x, y, want to like write some number, random values, generate some data in array. Yourself, whatever you want. Then apply KNN and evaluate the performance. Write the metrics.